Hi everyone. In this video we are going to look at the complex zeros and what is called the fundamental theorem of algebra. So we take motivation from some examples that we've seen before where we have looked at the number of real roots using Descartes' rule of sign. Now using a very simple example of quadratic functions, here are some cases where you have two intersections or two real roots, one intersection or one real root, and zero intersection or zero real roots. It becomes pretty obvious when you draw the graph that that is the case. Now, however, characteristically speaking, these are all parabolas, right? So they should all have similar properties, meaning they should all be, so for example, this can be factored as x minus 2x plus 2. This is just x minus 0 squared. But this cannot be factored with real numbers, right? But there must be a way to factor this if we can write 4 as the negative square of something. And this is where complex numbers come into play. Because I can write 4 as negative 4i squared, because I squared is negative 1. And then I can use the difference of squares to factor this in this manner. Now it will have two complex roots. So essentially what this shows us is that once you find the number of real roots, whatever remain, that have to be the complex roots. And that is what the theorem says. The theorem says that every polynomial with complex coefficients has at least one complex zero. Now this is a simplified formulation, but it's really powerful, right? Because every real number is also complex. So this holds for all polynomial. So what happens is, if you start with a polynomial and you have one complex zero, then the remaining part, you can apply the same theorem. And so eventually, a consequence of this is that every polynomial can be written as x minus c1, x minus c2, dot dot dot, x minus cn, where ci are complex. And complex can also mean real. So basically it says that a degree n polynomial has n roots or zeros, counting duplicates. Now what does this counting duplicate mean? If you go up here, you're like x squared, right? The zeros are just 0, but there's two of them, right? So that it still has two roots. And that is what is meant by counting the duplicates. So sometimes you may have multiple zeros happening at the same root. And which you have seen earlier in drawing graphs, it can either cross or it can turn around, right? Depending on the odd or evenness of the degree. So you can have multiple zeros. However, theorem says that if the degree is n, then there can only be a total of n zeros. So if the degree is 6, there can be 6 zeros. There might be a bunch of multiples in there, but when you count these duplicates or the multiple ones, it should still come out to be 6. So this, combined with the Descartes' rule of sign and the upper bound lower bound theorem, all of these give us a lot of information about what zero is real, what zero is complex. And in addition, it helps us completely factor certain equations that we may not have been able to completely factor previously. Let's look at an example. Find all the zeros of this polynomial. So here, we don't know. We're just going to go ahead and try some of the things that we have learned. Okay, so maybe it says find all the zeros. So let's look for rational ones, right? Now, if I look at the rational ones, then that's going to be plus minus 1 or plus minus 3. So 1, negative 3, 1, negative 3. I go with 1, 1, 1, negative 2, negative 2, negative 1, negative 1, negative 4. Negative 1, 1, negative 1, negative 4, 4, 5, negative 8. That doesn't work. 3. Actually, let me do 3 down here so I have enough space for the remainder of the problem. 3 is 1, negative 3, 1, negative 3, 1, 1, 3, 0, 0, 1, 3, 0. That works. So x minus 3 is a factor, right? So px is x minus 3 times the quotient, which here is x squared plus 0x plus 1. Now for zeros, I'm going to set this equal to 0. The first one gives me x equals 3, no surprise. The second one gives me x squared plus 1 is 0, or x squared is negative 1, or x is square root of negative 1 plus minus square root plus minus I. So the zeros are at 3 plus I and negative I. So there are, as you can see, the power is 3, right? So it's x cubed. So there has to be 3 if we allow complex numbers. And when we allow complex numbers, the factoring, the second one, gives us x squared plus 1 equals 0, which results in x being either I or negative I. Now for multiplicities, this is fairly straightforward in the sense that we've seen that this happens when the power is even, and this happens when the power is odd. So that's the definition of multiplicity of zeros. It basically means that there may be situations where one particular zero has a higher power associated with it. For example, if this is a polynomial, then the multiplicity of x minus 1 is 3 because it has 3 copies. Multiplicity of x plus 2 is 2, and the multiplicity of x plus 3 is 5. Graphically, what does that mean? It means at 1, you either have a this or this structure, right? At negative 2, you have a this structure, and at negative 3, this or this, you have one of these structures. Next example says, completely factor and find 5 zeros of this polynomial. First observation is that there's an x in each of them and a 3. So I factor out the 3x to get x to the 4 plus 8x squared plus 16. Now I'm going to first try and see if I can do something with it without the tools that we learned. Meaning, is there a way I can factor x to the 4, 8x squared plus 16? Now if you think about it, 16 is 4 squared. So this actually fits in the pattern of 2 times 4 times x squared plus 4 squared. I guess it would make sense if I write x to the 4 as x squared squared. This falls into the pattern of a squared plus 2ab plus b squared. So we get 3x and we get x squared plus 4 whole squared equals 0. So that obviously gives me x equals 0, that's 1. And the next one is x squared plus 4 equals 0. But this has a multiplicity of 2. And this, when you solve, is going to give you plus minus 2i. Okay, so the zeros are 0, 2i, negative 2i. And the multiplicity is 1, 2, and 2, so that when you add the duplicates, 1 plus 2 plus 2 gives you 5, which is exactly the power of the, or the degree of this polynomial. Now sometimes you may also be asked the reverse problem, namely find polynomial with specified zeros. So for example, find a polynomial of degree 4 which has these zeros. Now we use the definitions in reverse, namely if the zeros are these numbers, then the factors are x minus the zeros. So it's x minus I, x minus minus I, x minus 2, x minus minus 2, which is x minus I, x plus I, x minus 2, x plus 2. Right, so for this out, that's a plus b, a minus b, so it's x squared minus I squared. Same here, x squared minus 4. So that's x squared plus 1 and x squared minus 4. That's x to the 4 minus 4x squared plus x squared minus 4, x to the 4 minus 3x squared minus 4. The last thing that we need to check is we are given this condition that p of 3 should be 25. Let's see what that comes out to. 3 squared minus 4. That's 81 minus 27 minus 4. That comes out to 50. Right? To make this 25, we need to divide by 2. So the final px should actually be half of x to the 4 minus 3x squared minus 4. Why does that work? That works because by multiplying everything by 1/2, I am not really changing the zeros. The factors remain the same. And by multiplying by 1/2, I'm ensuring that this particular condition is satisfied. And the condition is that the polynomial evaluated at 3 is 25. So that's how it works. And you will notice here that these complex roots, right, in both these examples appeared in pairs, right? So you have I and minus I, you have 2i and negative I. So this even thing is actually a fact, is that the complex zeros appear in pairs. And these pairs also have a specific structure, which is something that you've learned in complex numbers before, called conjugates. So it so happens that if z is a complex zero, then so is the conjugate of z. Okay, what is conjugate is, for example, 2 plus 3i, then the conjugate is 2 minus 3i. Negative 1 minus I, the conjugate is negative 1 plus I. So what you do is you switch the sign for the I term. That's how it works. Let's look at, I believe that's the last example. Yeah. Find a polynomial of degree 3 which has zeros 1/2 and 3 minus I. Now here we are given only two zeros. But since 3 minus I is a 0, so is its conjugate. And what is its conjugate? That's 3 plus I. So the polynomial is x minus 1/2, x minus 3 minus I, and x minus 3 plus I. That's x minus half. So again, it's a minus b and a. Oh, it's not. We got to rewrite it a little bit. X minus 3 plus I, x minus 3 minus I. So now it is to become x minus 3 squared minus I squared, x minus 1/2, x squared minus 6x plus 9 minus 1, x minus 1/2, x squared minus 6x plus 8, distribute x cubed minus 6x squared plus 8x minus 1/2 x squared plus 3x minus 4. So it's x cubed minus 13 over 2x squared plus 11x minus 4. So that is essentially the reverse problem. Given zeros, you're asked to find the polynomial. Now where is that useful is if you are in a situation you're modeling something and you know that that particular function has to equal 0 at certain inputs, then that is where you can find the form of the function subject to a bunch of other conditions. And if you are given some of the complex zeros, then you just need to use the fact that the complex zero and its conjugate are both zeros for the polynomial. So that works out fine. That's it for this week. That's the last video, and you can go ahead and try the worksheet as well as the homework. Thank you.